happened with Colin Wessler as well. He then came to Oregon State to work with us. He's been studying processes having to do with the inorganic particles we're discussing, mostly inorganics. They have organics with them. And he gave a talk to the previous class, and they really like it, so we decided that you guys should benefit from it as well. Anyways, and he'll be with us all day long, including this evening. And this evening we're going to have a little feast. There's oysters coming, and I'll bring some wine, and others can bring some wine.
I'm leaving before then.
No.
Yeah.
I made a bet for you. You're not.
I am. Yeah. Well, I came down from a family place, and my sons are there, and there's reasons I want to be there. I love being here too. But anyways, I left with plenty of time to get down here, and I committed the cardinal sin that our generation tells your generation never to commit, which is you should always have a map. Well, I didn't have a map. All I had was my memory, and it was a tiny bit flawed. I got to the post office, had this crisis of confidence in my route, tried to use the phone, no service, so I had to go all the way back out to the market there. Anyways, I got here on time. It's really fun to be here today to talk to you about using optics to characterize sediments. Not so long ago, people would have wondered why you would have a sediment person in a room full of people interested in optics. That's because really with the advent of satellites, so much attention was focused on explaining the color of the ocean on really large scales. And as you know, that's an absolutely fascinating topic. But certain people, led an awful lot by Ron Zaneveld at Oregon State, recognized long ago that sediments have different optical properties from water and other constituents in the water, so that optics could be a useful tool. And this is just a great demonstration of that, unfortunately with negative environmental implications. This is in the north shore of Kauai in Hawaii, and there was a rainstorm in the watershed, as there often are, but poor development practices put a lot of sediment into the runoff now. So you see nice, beautiful sediment laden water mixing up with this ugly oligotrophic water right here. You know, it doesn't take a genius to realize that sediments have different optical properties. So Emmanuel and I have been working together for a long time. My angle was, why do optics work at all for characterizing sediments? And Emmanuel's angle, along with others, was how can we expand the use of optics to really characterize sediments? So why does sediment matter? I won't talk too much more about this, but suspended sediment blocks light, so it matters to phytoplankton and other primary producers that live on the bottom. It also is ugly to many people. Suspended sediment carries lots of pollutants, and deposited sediment takes up space, so it's an issue for keeping harbors dredged. This is an image not from the ocean. This is the Great Lakes, this Lake Ontario just north of Toronto. And thunderstorms had introduced a whole bunch of sediment into the lakes, and there's all sorts of cool stuff going on there. So why would we use optics to study sediments? It's a great deal because the collection of sediment is difficult. This is what you have to do. You have to go out in extreme environments and have your sheltered friends laughing at you while you're doing it. And sediment transport is also a world of extremes. The amount of sediment that you carry in the water goes with the cube of the velocity. So it's when the velocity is big, you carry lots and lots of sediment. So you need to be out there in extreme conditions to observe sediment being transported. Also, characterization of sediment is time-consuming. The normal old-fashioned ways, you collect water, you filter it, you weigh the filters, you do the size distributions. All of you should have to do this at some point in your life, but hopefully you won't have to do too much of it as I have. This is just a cheap way to put in a video. I'm going to show you sediment transport in extreme environments if I get my cursor back up here. All right. This isn't my environment. This is also on the north shore of Kauai. These are big waves. There's a little person over here. And the really interesting thing about these waves are these puffs of sediment in them. Not how big they are or that there were humpback whales leaping in the distance behind them, but they really are big waves. And obviously you can't get in waves like this and make observations of sediment transport. You need some kind of remote method to do it. And optics provide just that kind of method. I think the next wave has a nice... Anyways, you can see all sorts of good sediment transport. There's a good sediment puff coming up in this one. See all that through the middle. So there's no way you're going to get that by just trying to collect water. Two goals for this talk. I gave a talk a few years ago, and I said to Emmanuel, trying to be lazy, I said, that talk was good, right? And he said, no, you need to make it much more general. So I'm going to try to give a more general sediment transport talk, because he said many of you have never thought about the fact that you could use optics to study sediment. So what I'm going to do first is review the basic principles linking sediment and optical properties. And we're going to go over 3 principles that are really important. And then what I'm going to do is present an application of these principles, which is part of Jing Tao's PhD project. She's a student with me. She took this class a few years ago, benefited greatly, and now she's applying these principles in the real environment. Okay, so important sediment properties that we want to know about. You could really just distill it down to we care most about vertical flux. Okay, there's other things we care about. But vertical flux, I'll just put this up here, is the product of the settling velocity, Ws, times the concentration. The settling velocity is given by this thing called Stokes' law that some of you may have been exposed to, which says that the settling velocity goes as the density difference of the particle, ρs, with the fluid, ρ, times gravitational acceleration, times the square of diameter. That's a really big thing about Stokes' law, is it says that settling velocity goes as d squared, times the concentration, that's not part of the settling velocity, divided by 18 times the dynamic viscosity. So if you want to know what vertical flux is, this simple representation of it says that you need to know sediment mass concentration, you need to know particle size, and you need to know particle composition. We have conventional ways of measuring these things as sedimentologists, but optics give us proxies for all of these. Okay, so the 3 principles that matter for characterizing sediments with optics. The first one, and this is the one that I've worked on the most, is that marine particles are typically aggregated. They're clumps of particles, not single solid particles. And in aggregated particles, the suspended mass scales not with volume like it does for solid particles, but it scales with the area. What else scales with area? Inherent optical properties, the attenuation due to particles scales with area. So what this is going to tell us is that mass can be figured out by looking at some inherent optical properties. The next one, these next 2 are ones that Emmanuel has worked on with others. Particle beam attenuation depends on particle size relative to the wavelength, and this is especially true at the small end of the size distribution and not so true at the large end of the size distribution. And then the last principle we're going to work on is backscatter ratio depends on the index of refraction of particles. Inorganic particles have high index refraction, they backscatter more brightly. Organic particles, low index of refraction, don't backscatter so brightly. Okay, so let's whip through those. For solid particles, conversion from an optical property to mass depends on particle size. And when I started grad school way back in the 80s, this was given again and again as the reason why optics shouldn't work, because we know particle size varies in the ocean as you vary the stress and vary the types of particles. So why on earth should you be able to use optics to say what mass is? So the real problem here is optical attenuation scales with particle area. For solid particles, mass is proportional to particle volume. So for solid particles, the ratio of attenuation to mass scales as 1 over d. So in order to go from an optical property to mass in the water column, you need to know what the size is. We often don't know what the size is. This little image here demonstrates that these BBs have the same volume as this BB here. But this has a whole lot more area. It's a little bit of a cheat because we'll put it down on one plane, but it demonstrates the point that you have a whole lot more area for smaller particles and larger particles. So why can we use optics to estimate mass? And it's because, as I said, particles, marine particles and a lot of freshwater particles are aggregates. They're not solid constant density particles. And what this image shows is some aggregates that we captured in this polyacrylamide gel. The flocks sink into it, the aggregates sink into it. I'll interchangeably refer to them as flocks or aggregates. They sink into this gel in seawater. As soon as it's exposed to air, it solidifies, crystal clear, and you can section it and look at it in microscopes. That's a 300 micrometer scale bar. And what you can see is there's lots of void spaces. Now the thing with aggregates is as they grow, they incorporate proportionally more void space. So what that means is that in aggregates, the mass on average is proportional to particle area. Now some really neat theoretical work was done on the computer and then with highly idealized particles back in the 80s that showed this was true in an ideal sense, and it works in the ocean as well. So how did we figure that out? We figured it out by making lots and lots of measurements of size versus settling velocity. So what we've got is settling velocity in millimeters per second on the y-axis, and we've got diameter in micrometers on the x-axis. Note that the axes are log, and this mess of points here is what you get if you go out and measure 21,000 or something like that particles for how big they are and how fast they sink. These are from all different environments, and if you run a line through that, boldly run a line through that, you get a slope of 1. Now this is log-log plot, so if you're doing a regression, what that should show is what the exponential dependence of WS on diameter is. I know you're remembering Stokes' law, and I made a point of d squared. That's what it should be for solid particles. This is what it always is for aggregates. So what that means is that the density has to vary inversely with diameter. So the basic distilled message from that is that mass goes as area. So if an optical property measures area, you can estimate mass. Okay. Now that's the reason why people, ever since transmissometers were invented and thereafter backscatter sensors, have been successful in relating mass, here shown in grams per meter cubed, to an optical property. Here's attenuation. So this is from an Alliance of Coastal Technologies data set that Emanuel and friends analyzed and published back in 2009. The same holds true for backscatter. Same holds true for side scatter. You get a nice linear relationship, and this linear relationship really comes from the fact that particles are aggregates. Okay, next principle. The next principle is that particles, attenuation depends on wavelength. What was the nice way I said that before? Anyways, attenuation has wavelength dependence, but that wavelength dependence depends on particle size. So this is from Wayne Slade's FastMe code. Have you guys been using that stuff? Have you done this me stuff? I'll just say yes. Okay, blue line, blue light. Red line, red light, special color coding. And what it shows is that if you're down in this region, down here, the shorter wavelengths attenuate more than the longer wavelengths do. So remember what the scattering efficiency is. That's what you have to multiply the total area in suspension by in order to get the attenuation. So if you look here, if you look at short wavelengths, at this particle diameter here, the red's going to attenuate a lot less than the blue is. Okay, so what you would get if you measured a spectrum is high in the short wavelengths, low in the long wavelengths. If you go out into this part of the particle size range here, I probably forgot to say what my axes were. This is particle diameter. Out here, everybody's the same. You go to geometric scattering, everything's got a scattering efficiency of 2, so it doesn't matter what wavelength you are. So that means if you measured the spectrum of attenuation, it would be flat. So if you have small particles, steep, big particles, flat. So we can use that to say something about the size of particles in suspension. And this is something that here's some famous people: Emanuel Boss, Allie Chase. Anyways, this is from the whatchamacallit, the Terra expedition. And let's just focus over here. This is wavelength. This is the CP here in this panel, and what you see, and then they normalize them down here. And what we see in the blue and the green, so this is going into more chlorophyll in the water as you go from blue to green to red. If you have not much chlorophyll in the water, bunch of small particles, you get these steep spectra. As you have more particles in the water, bigger particles, you get flatter spectra. So we can use this to say something about particle size. And Wayne Slade and Emanuel recently published this relationship in 2015 in Applied Optics. This shows the attenuation spectral slope, so how steep or unsteep it is, versus the average size of particles smaller than 50 micrometers. That 50 micrometer cutoff is because of acceptance angle stuff that we'll talk about later. But what it shows is a nice negative relationship, where as you go to bigger particles, you have flatter spectra. So we can use the spectrum of attenuation to say something about particle size. So we've got two now. Remember, we wanted mass concentration, we wanted particle size. We've got optical proxies for both of them. Now the last one is using backscatter to say something about composition. This is the Fournier-Forand phase function, which says what kind of scattering you're getting versus as a function of scattering angle. And the fact that I plotted this linearly hides some stuff going on here, but there's this blue line is falling below the red line up here, and then it's above the red line out here. The blue line is higher refractive indices. So what this means is that if you add up all the scattering from this part, the back scattering from here, and divide it by the total scattering, you get a bigger number than if you do the same for the red, which is a typical organic refractive index. So we can use the back scattering ratio, how much from here to here divided by the total, to diagnose whether the particles have a high refractive index or a low refractive index, and we can relate that to composition, which is related to density. And that's shown here from JGR paper from the dark ages of 2004, and it's showing the backscatter ratio here at 532 versus how much chlorophyll there is divided by the total attenuation. So if there's a lot of chlorophyll making up the total attenuation, that's organic-y waters, you get a low backscatter ratio. If there's not much chlorophyll in the water relative to the total attenuation, you get high backscatter ratios, so that's more inorganic stuff. So by using this ratio, we can say, is it more inorganic or is it more organic? Okay, so just to summarize that part, the optical parameters for sediments, and there's others, but these are the ones that I think are most useful. We can use attenuation or the backscatter coefficient to estimate mass concentration. We can use the slope of the attenuation spectrum to say something about particle size, and we can use the backscatter ratio for particle composition. And you can make all of these measurements with a few instruments that are easy to deploy, especially if I don't have to deploy them. They're really easy to deploy. So this is the Bay of Fundy. Highest tides in the world. This is the Minas Basin. There's Cape Blomidon. And you should come visit here because it's a nice place. That's the only reason I have it up there. It's what's separating Maine from Nova Scotia. But really why I have it up here is look at those waters. Those are beautiful, high inorganic content, high sediment load waters. Okay, so now what I'm going to do is pause and say, is everybody okay with the principles, what we're working on here? Questions? Okay. Now we're going to shift to, yeah, Emmanuel?
The least itself does science better than volume times resounding.
That's right. That's right. So yeah. So we'll see some instruments that I use. The instruments that I use do a really good job of particle size, or no, they do an okay job of particle size distribution, better than just using the attenuation spectrum. The idea is to move to instruments that are more compact, and you'll see our instruments are bulky, more compact, more economical, so you could deploy a lot of them, so you get long time series, however you need to get long time series. So we have tools as sedimentologists that do all of these things better, but the idea is to try to use optics to do it as simply and cheaply as possible. Okay? All right. So now we're going to talk about this, this study the data were actually collected by Emmanuel and Tim Milligan and me, but they've been analyzed by Jing Tao for her PhD project. And they come from the mouth of the Columbia River, which, as many of you may know, the Columbia is a big river that drains through Canada and the interior of the Pacific Northwest and comes out at the border between Oregon and Washington State. This was a Office of Naval Research funded project. This is a really extreme environment, and it's a type of environment that the Navy would like to figure out things about without having to send wet scientists there. We did a bunch of looking around in the river, characterizing the optical, simultaneously characterizing the optical and particle properties. The data we're going to talk about come from right in the mouth at an anchor station that we occupied for a few hours. But as I said, the mouth of the Columbia River is an extreme place. This is a ship transiting outwards. It has really interesting dynamics. It's a massive river. It has really big tides, 4-meter tides, and it has big waves right at the mouth. So on peak ebb tides, you can have breaking waves that are, 7 meters high right in the mouth. This is the place where you've seen those lifeboat rescue things where the lifeboats are getting, flipped over in the waves. This is where this happens. So this is a really extreme environment. It makes it an environment that's very challenging to make observations because the conditions are so ferocious. And because of that, we don't have very many observations. And it's really ideal for new in situ and remote sensing technologies. And this is why the Navy had us go there. So overall, the goal of our work and the goal of the Navy in funding us is to link these 3 bubbles in any way that you want to. So over here we've got the optical properties of the water column. Over here we've got the sediment properties. And here we have remotely sensed properties. So the idea is that if you knew or modeled any one of these, you could make links to the other ones. So if I had what I thought was a good model of particle properties, I could forecast what the optical properties were, and then we could say what you would see from space. So that's the general idea. Today, what we're going to do is just stay down on this arrow here, linking the optical properties to the sediment properties. Now, I know the whole title of this class is this one, right? So just forget about that, okay? We'll just stay on the horizontal here. Now, a whole lot is already known about sedimentation in estuaries, and the Columbia is no exception. The exception with the Columbia is a lack of data because it's a fierce place to work. This is an image from Dan Nowacki's paper in 2012 where they did transects offshore of the mouth where it's not so fierce, and what they saw was really rapid sedimentation from the plume, more rapid than is typical of rivers. And they argued that there was intense resuspension of sands at the boundary between the salt water here, a salt wedge here, and this really rapidly flowing fresh water here. So that was the specific basis for our work, was to test whether we could see whether that intense resuspension was going on in the mouth with optics alone, but with the companion particle studies. Overall in estuaries, what happens is you have fresh water coming in from the river, and that fresh water rides up over the denser salt water. There's some mixing that occurs between the fresh and the salt water, and that depends on the strength of the river flow relative to the strength of the tides. If there's mixing between the fresh and the salt water, what you get is landward flow in the near the seabed to balance that transport of some salt water out as it gets entrained into the plume. So why that's interesting is particles settle out of here, out of the plume, into this landward flowing water, and typically you get a region of enhanced sediment concentration there called an estuarine turbidity maximum. So that's your brief tour through estuarine sedimentation. Point is, we know a lot about it, so we weren't going to rattle the cages of the sedimentation world by doing this study. what we set out to do, in part, was to show that you could use optics to document these sedimentation patterns with optical tools rather than conventional sedimentology tools. Okay, so here's our equipment. So what we have is a flock camera. This is a beastly big thing. Have you been using a list? You know how big a list is? So there's the flock camera. It's bigger than a list. And there's reasons why it has to be that big to take good pictures of the particles. But it doesn't really have to be that big. But anyways, so we use the flock camera to look at big particles. We take silhouette images, so they're backlit. You see the outlines of the particles. You estimate what their volume is based on their area. We use the list here to measure the small part of the size distribution. And as you know, that uses near-forward scattering and inverts the scattering pattern to give you the size distribution. And then we merge them, and I won't go into the details of that, but we merge the size distributions right around the 63 micrometer size range, and that I just won't say anymore. We've thought a lot about it, but you don't need to. The list also does beam attenuation. So the idea was to use the beam attenuation from the list to estimate what the concentration was, and then we would measure the size distribution with these two instruments together. We used regular old Niskin bottles to get the water samples. Oh, I've got nice little labels here. So there's the list. So Niskin bottles to get direct estimates of what the mass is. Then we had the AC9, and as you know, the A is for absorption, the C is for attenuation, and we did this filtered and unfiltered to get at what the particle part of absorption and attenuation was. And then there was, there are the Niskin bottles, and then there was a BB2FL to get backscattering at a couple of wavelengths, as well as fluorescence. So that's the instrument package. The part of the study I'm going to talk about, we were just sitting in an anchor station and profiling it over course of time as the tide came in.
There's an automated switch, which is important.
There's an automated switch, which is important. Yeah, so it...
We don't have the time to take the package out and put figures and bring it back.
Right, so as it goes down to a certain depth, it goes to filtered. So on the way back up, you get a measure of what's dissolved in the water column, and then the switch goes again, and you can do another profile and get the total. So you get the total attenuation and absorption, and you get the filtered attenuation and absorption. By differencing, you get what the particle load is. Okay, so couple of things here. I know you know about these instruments, but so we use the list here. Here's the business end of the list. It doesn't normally have this this box on it. That's for getting Z-scats in the lab, but it measures the particle size distributions, and it does attenuation at 650. And then here's the AC9. Big difference with this is it sucks in water. And then looks at the absorption and attenuation in a tube, and it pumps the water through that, and that'll become important later on. Generally, someone like me is going to say, that's bad, because those little fragile flocks I had, those things that I look at, they get destroyed when you pump them through things. So normally I would be saying that's bad. By the end of the talk, I'm going to be saying that's good. And a key difference between these two instruments that's going to be important is that the list, because it wants to measure as big a particles as possible, which scatter in the very near forward, has a really small acceptance angle. So if you're just a little bit off of going straight ahead with a light beam, the list is going to detect that as scattered light, whereas the AC9 has a wider acceptance angle. Anything that's coming in from this relatively larger range of angles, the AC9 is going to say, that wasn't scattered, that was actually transmitted. So that's going to come up later on. It's going to come up right now. The AC9 has a larger acceptance angle than the list. Okay, so there's two parts to this study. The first one is a cautionary tale. Okay, if you had asked me before this study, I would say absolutely you should use list attenuations because they are better. They have a smaller acceptance angle, so you're going to get more of the scattered light registered as attenuated. But this small acceptance angle, it turns out, causes some problems in my kind of environments where there's steep density gradients in the water column. So that's the first part, what we're going to talk about here. Okay, so what we found right away when we looked at these data was that the mass was not proportional to the attenuation of the list. Okay, so immediately what I thought was, oh, here's this old ugly problem of size distribution rearing its head. Why would it rear its head here? The Columbia is not a very muddy environment and it's very energetic, so it can actually resuspend sands off the bottom. So it's like, all right, we have a problem in that we are seeing solid single particles that aren't getting picked up by the optics very much, but they are heavy, they are massive. So to look at that, what we did was say, well, that shouldn't be a problem if we plot up the total area concentration versus the optical property versus attenuation. So we expected when we plotted up total area concentration instead of mass that we would get a nice straight line plot. Because for these big, if it really was these big clunky particles giving us problems, they should be geometric scatterers and you should get this nice proportionality between attenuation and area. But we didn't. We got this total mess here. So that told us something else was going on. It couldn't have been a size effect. Something else was going on. And what was going on was this. This is an image from our camera, and what these beautiful diaphanous images are here are the manifestation of mixing of fresh water and salt water that's producing rapid variations in the index of refraction in the water, and it's an effect called Schlieren. You're most familiar with this, seeing it on rising over a hot roadway in the summertime where you're getting this light getting scattered around by the hot air mixing with cooler air above it. But it happens in estuaries, and it happens at pretty low buoyancy frequencies, which we'll talk about. So what's going on here is that this mixing here is making the light beam go like this, and we're picking up false attenuation, false particle attenuation. So this is where the acceptance angle things come in. Okay, so the AC9 has a large acceptance angle. The list has a small acceptance angle. If we just have a large particle here that scatters in the near forward, what happens is that some of the light that is scattered by that particle makes it into this acceptance angle and gets read as transmitted light. So if you have a large acceptance angle, that's going to be more of a problem for large particles. If you have a small acceptance angle, much less of the light that's being scattered by that particle is going to be misread as transmitted. So that's why I would normally say the list is a better instrument for measuring sediment stuff. But now if you have these density variations, the Schlieren represented by this green bar here, if you have a large acceptance angle and the Schlieren is steering your light beam around, more of that light that's being steered around by that density mixing is going to be read as transmitted, which it should. It's not particulate scattering, whereas you have a small acceptance angle like the list, it sees that as scattered light. I'm using attenuation and scattering interchangeably, and I'm doing it because that's kind of my world. I don't deal in environments that are really biology rich, so I apologize for that, but you'll have to forgive me. Yeah, Emmanuel.
The other advantage the AC9 has for this flaring issue is the mixing as you draw water through the flow tube.
Yes.
The list is open to, so.
It's like my next slide. That's all right. What Emmanuel said is true, which I normally would also view as a real problem for sediment stuff. Like, I don't want to mix stuff up and break particles. So anyways, as the acceptance angle goes down, generally beam attenuation goes up. Okay, so this is back to our total area concentration versus CP. I did this is what our size distributions look like in the Columbia. This is diameter in micrometers versus the area concentration in millimeters squared per liter. Yeah?
Is that really, I mean, is there something geologically meaningful about the fact that you have peaks in the area concentration at two different diameters and lower areas in between?
Yeah.
Or is it that you're at the limits of your instrument?
No, it's not, because in a more typical environment than this one. This would be flatter across here, or you would see. So what's going on here is that the Columbia is really productive at this time of year. So it was in June. Columbia is really productive. There's a lot of small guys or big guys in the plankton. I'm talking biological. So there's some biology going on here. And this is my flocky, sandy stuff out here. So that's why it's bimodal in this case. A normal, what I would look at as more a normal sedimentary environment, you wouldn't see such a big peak down there. Okay, so that's what that is. Here's that total area of concentration versus the attenuation. And what we see is what we'd like to see for a lot of the points, and then you've got these guys here where there's a lot of attenuation, but we don't see any evidence in the particle size distribution that attenuation is due to particles. So what we looked at was a postdoc who worked for me and then worked at Sequoia and now is over in Denmark, Ole Mikkelsen, looked at buoyancy frequency as a diagnostic for when this would be a problem. So what's buoyancy frequency? It's gravitational acceleration over the density of the fluid. The key here is that it characterizes the steepness of the density, vertical steepness of the density gradient. So if density is changing very rapidly with depth, you get a high buoyancy frequency. And what that means is if you pulled up a little bit of water from below and let it go, it would go bounce fast. If you don't change density very rapidly with depth, you get a low buoyancy frequency. That means if you pulled up a bit of water from below and let it go, it would do this nice big, long up and down. So low buoyancy frequency. This is big, or when this is big, you're going to have Schlieren problems, okay? That's when you have fresh water sitting right on top of salt water, and when you mix them, it's going to do that weird Schlieren thing. So if this is big, Schlieren should be a problem. If this is small, Schlieren shouldn't be. So what Jingtao did was just stratify the data based on the buoyancy frequency. And what she found was that if you had buoyancy frequencies that were less than 0.05, which actually isn't too big a buoyancy frequency, and you plotted those data up, you got this nice linear, as expected relationship between total area concentration and attenuation. The higher buoyancy frequencies exclusively were the ones that were sitting up here. These ones where you were saying, according to the optics, that there was particles around, but the instruments that measure particles said there weren't particles around. So this is good indication that it was the Schlieren effect that's causing those spurious points there. Okay, so what we did then was do the same thing with the other instruments that we had that measured an optical property that we could relate to mass. So here's the list attenuation. Here's the AC9 attenuation. No effect. Nice, as expected, linear relationship between total area concentration and the attenuation. And there's two possibilities for why that is. The first one is that it has that larger acceptance angle. So if I'm just shooting a beam at Mary Jane and it's just going a little bit like this, if you have a small acceptance angle, that could get interpreted as attenuation. Large acceptance angle, you say, oh, no big deal. And then here's the point Emmanuel was making, is the list measures water in situ, the AC9 measures mixed water. What happens during the mixing is it gets pulled into the tube. All that Schlieren gets mixed away in that nice little environment of the tube, so you don't have any Schlieren effect inside the AC9. Could we test that by taking the tube off? Yeah. Yeah, so that's indirect evidence. We have tested it with backscatter where we've actually mixed up made Schlieren and seen whether the backscatter had an effect, and it doesn't. Backscatter's right on. Okay, so no problem with backscatter either. It just doesn't get affected. So if we go ahead and correct the list CP data, and we plot up the AC9 CP data and the backscatter data from the BB2FL. What we see, this is SPM here. Just worry about this side of the plot. I think, oops, there we go. What we see is great correlation between CP and the mass of sediment in suspension. And that's for all three instruments as long as you correct the list. The problem in correcting the list is you throw out a bunch of data. So it is not the optimal instrument for measuring CP in these environments. Okay, so that was the part one, the Schlieren effect in CP. Part two is variability of the particle and optical properties at this anchor station that we occupied in the mouth of the Columbia. Okay, so there's the anchor station right in the mouth. It's a fierce environment. I went on board the vessel as we were transiting. I went on board the bridge as we were transiting out of the mouth on an ebb when you can get these really big waves. And it was kind of the check in with who was at the controls, tell them what we were up to. I remember walking up the gangway, and the second mate, who was not the most confident pilot, turned around and his eyes were like dinner plates, and I looked out in front of him, and there's just these enormous short wavelength waves coming at us, and the boat's just going through them. Anyways, it's a violent place. So what we did was occupy an anchor station in a not thoroughly violent time, and so we're going through time here. What it looks like is a spatial image of a salt wedge, but what we're seeing is as so we were here, and then the tide started to come out. So what you see through time is that the fresh water is eventually coming down to our site, pushing the density interface from upriver down to our site. And this density interface is a scene of intense physical processes. The seabed just basically gets blasted there. Rocky Geyer calls it like a snowplow, just snow plowing back and forth along the bottom. Here are our SPM observations, and this is great because it shows what the problem with our conventional methods are. These data were won with a lot of hard, boring work, and there's not very many of them. So we get a bottle at the surface, a bottle at 5 meters, bottle at 10 meters. Here's the companion backscatter data, which are much easier to get. You still have to be out there, in this case, getting them, but the later analysis is big. We, as you saw in the last slide, we did the correlation between the backscatter and the SPM. So we used these backscatter to produce a map of what the concentrations were. That says diameter. I better see whether that's true or not. D. Yeah.
SPM.
Yeah, it's SPM. Ah, panel D, thank you. Can you tell this is Jing's talk, not mine? But and what we see is, if you think back to that image that we had, that gray image from Dan Nowacki, what he inferred was that there was a resuspension occurring at the density interface. That stuff was getting transported out in the plume over the underlying salty water, and then that material was sinking into the landward flowing salt wedge there. Okay, so this just goes over it a little more. So this is the velocity associated with the tides going in and out. So what you see is that we were in this ebb where the water was flowing out, which is what brought this density interface to the site. Okay, so here are the optical proxies. This is the backscatter. This is the Souter diameter, which we generated with our instruments. It's really a ratio of volume to area. It's a good way to characterize the size of particles in suspension from a full particle size distribution. This is the spectral slope right here, and this one is the backscatter ratio. So remember what our proxies were from our three principles. We can use this to estimate mass. We can use this to estimate size, and we can use this to estimate concentration. So this one's the easiest. If this is big, the suspended particulate mass is big. And what we see is that at this density interface, there's intense resuspension of particles as inferred by Dan Nowacki and observed in other estuarine environments. If we go down to gamma and ask what is the size of those particles, these red mean a big gamma, and the blue means small gamma. So what does big gamma mean? Anybody remember? Big or small particles? Got a steep spectrum, small particles. So we've got these particles that are being resuspended are relatively small. Now, does anybody have an idea for why that would be? Okay, these particles are aggregates. I said they were fragile. Yeah, they're just getting destroyed in this intense density interface here. So you get these large gamma values. Now, look out here, we've got these big gamma values. Why do we get big gamma values out here? Huh?
It's a stable environment.
It's a stable environment, but in estuarine sedimentation, what happens is the particles aggregate in the plume here. They reform those big flocks, and they sink. The bigger flocks sink faster than the littler ones. So what we're doing is we're capturing those larger aggregates here. That's moving us out into that flat part of the spectrum world, so we get lower gammas here. So that's beautiful. Now let's look at the backscatter ratio. What does high mean? Anybody remember? Which particles are brighter in the backward direction? The inorganic ones. So high means inorganic sediment, low means more organic sediment. Where we get the higher values is near the bed, where you're having this intense resuspension of small particles. And then we also get big values out here because it's those little small particles that are reaggregating and falling into the seawater here. Colin?
How come you don't have the subtle diameters in that intervening region in there?
That's a great question. Can anybody think why we would not have Sauter diameters in that intervening region there? Where would the buoyancy frequency be really large? Right here. Where does the list fall on its face? I didn't go into this. I removed one slide, and it was showing that size distributions are also affected by the Schlieren. So we have bogus list size distributions in that area too. I didn't want to offend any Sequoia people too much about that. So it screws up the size distributions too. So anywhere where there's a high buoyancy frequency, we had to throw out the size distributions.
The
Yeah.
measurements you made with the AC9, with the AC9, right?
Yeah.
So those have all been broken. The big box should have been broken up by the time we got into the AC9.
It's a good question, but we see clear. So maybe the biggest guys are broken up, but they wouldn't register on the AC9 anyway. So what we're seeing is a pattern that may not be revealing exactly what reality is, but we're seeing a pattern that there's bigger particles here than there are here. It depends on what kind of shears they're experiencing in the AC9. And Wayne saw this in his paper, so that was going through the AC9 as well, and saw this obvious link with size. So.
Basically, you're saying that the large particles that the AC9 is seeing are related to the even larger particles that it's not seeing. So you're taking advantage of the fact that it's a size spectrum continuum.
That's right.
Although you're not measuring the big aggregates, you're measuring something that's covariates with that.
That's right.
So.
Yeah. Yeah. And I have another student, this was stuff I didn't have time to talk about, who looks at the volume of list size particles relative to the total volume, and they are right on as long as particles don't get too big. But anyways, that's nice. Yeah.
So here you're correlating backscatter BBP with SPM. But I thought I saw on a previous slide too that you were doing CP with SPM as well.
Yeah.
That correlated pretty well. So did you find that one is better than the other?
In this study, they were pretty even in terms of the correlation. We were going with the BBP because it's unaffected by Schlieren, and it's also on raw water, so it hasn't gone through the pump. But really, one was not better than the other. In some work by Greet Nuckermans and by Emanuel, backscatter tends to be more robust as a measurement. For sedimentologists, they like backscatter because it works better in highly concentrated environments too. So you don't run into the problems with getting maxed out with your attenuation. So that's why I put it here. Did something change? Oh yeah. Okay. Larger particles, smaller particles. More organic particles, mineral particles, okay? And I alluded to this before, the Columbia is really productive. So as we went upriver, we had low backscatter ratios and relatively high concentrations, and high chlorophyll. Okay, so to summarize, attenuation and backscatter coefficients are good proxies for mass concentration, and the slope of the attenuation spectrum is a good proxy for particle size, and backscatter ratio is a good proxy for particle composition. The Schlieren is a problem. It's not going to be a problem for some of you, but many of you it could be, because we found that it's at pretty low buoyancy frequencies. And in working on writing up this paper, Emmanuel and Jing and I have found some examples of nice open ocean environments where the buoyancy frequencies are high enough to affect attenuation. And in those environments, these particle layers are being invoked for which there is no good physical explanation or any other supporting data. So that's a problem. Some people will may be unhappy when we talk about that. You can use attenuation in these environments, and you can use the list in these environments, but you have to pay attention to your buoyancy frequencies. Schlieren do not affect the CP and the backscatter derived from the wet labs AC9 and the BB2FL. This probably because of acceptance angle and mixing, and this because backscatter doesn't care about Schlieren. Kurt, you probably know, but I don't know why, but it doesn't care. So in summary, an accurate understanding of key sediment properties can be developed with optical measurement. So did we develop a completely different understanding of sedimentation in the Columbia estuary by deploying these optical methods? No. People have been working in this estuary for decades. Did we show that you can use optics to produce the same understanding of what's going on in there in a much more economical and simpler way? Yes. And we did it, and it shows that you can get much better coverage than is available with typical sediment methods. Okay, that's what I've got.
Yeah, the reason backscatter doesn't care about Schlieren is these, you've got a small gradient in the index refraction, which just steers the thing.
Yeah, it doesn't send anything backwards. Yeah. 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 That's good. That's good.
Does the list have segmented, it has the segmented by angle or by scattering angle? Is that segmented as weekly also?
Yes.
Yeah.
So you'd see the Schlieren is sort of as usually dependent.
But it doesn't measure all quadrants, so it's not like it takes the ring at some angle and measures all around the ring. It only measures some chunk of it like this, and then the next ring it's measuring the part down here. It doesn't measure.
Enough that you can
Nope,
see
which
these.
is really unfortunate actually. That would be cool. So do you still filter samples?
Do I? No. I try not to. No, I still filter samples. I mean, you always have to ground truth the stuff. So yeah. But I mean, this is a good example. So we didn't do tons and tons of filters here, but we did. We did enough to ground truth our observations. But
Do you have some evidence from these samples about organic rich versus more mineral to back the backscattering ratio observation? I know you do loss of emission sometimes. So.
yeah, and we ended up. I'm fumbling because I don't remember whether we did 2 sets of filters on these. I don't think we did. I think we should have, but we didn't. I don't remember. But at this point, no, we don't have any. I mean, we can look at chlorophyll and show that it's going with the chlorophyll, but same thing you were doing in that other one, chlorophyll versus total CP. But we don't have. I don't think we did the extra filter samples. I don't remember doing them. Anything else? Okay.
So Paul would be